Hi, we continue 7.4 ordinal multinomial responses. So last time that we studied the proportional odds model. So that was the G of gamma j is equal to the theta j minus the beta transposed x. So here the gamma j is probability of y is less than j, and the y is an ordinal response variable which can range from 1 to j. And this time that we have the j here. So actually the coefficient of x also depends on j. So last time, the proportional odds model, that was using the fixed beta. So that means basically, okay, so we have the response variables, several predictors, and we can actually think about the kind of parallel lines, because the beta transposed x and the beta is always the same, and different theta j's. So that means, okay, so we have the parallel lines, and this is a space of predictors, and here that we categorize observations as 1 and 2 and 3 and 4. But we assume that this, the thresholds are parallel for all categories. But here that we have the beta j transposed x. So that means the slope for kind of the normal vector for the space is actually different for each j. So that means if we have, okay, x1 and x2, it's possible to have the different lines. So this is 1 and this is 2 and this is 3 and this is 4. So this kind of the criterion is possible. So it's a little more general, but the expense is that we have more and more parameters. So if we have, for example, the two predictors, x1 and x2, and intercept, for the proportional odds model, that we only have few things. So we have if we have 4 categories, we have the theta 1, theta 2, theta 3. So we have 3 thresholds, and the coefficients for x1, so that is beta 1, and coefficients for x2, so we have beta 2. So we only have these ones. But here, if the generalization of proportional odds model is used, we have the theta, excuse me, theta 1, theta 2, theta 3, and also x1, the coefficient for x1 is different for each model. So I would say the beta 1,1 and the beta 1,2, beta 1,3, and also the coefficient for x2 is also different. So beta 2,2, beta 2,2, beta 2,1, 2,2, 2,3. So we have in total 9 parameters. So the number explodes if we have many categories. So it's a kind of similar to multinomial, the logistic model. So it's a little bit, against the idea of ordinal model, because we have response variable is ordinal, then we can save some parameters. So that is the one unique feature of the ordinal models. But here, that we go back to multinomial model basically, and then estimate it. But still, it's ordered. So we estimate probability of y is less than or equal to j. So we still keep the ordinal feature. Okay, so here is the example. So last time that we used the MASS library and the POLR function, but here we cannot use that function anymore. So we use this VGLM package. So GAM is the generalized additive model. So this is the case that the is represented by the f of x1 plus f of x2 plus f of x3, and f is pretty general function. So this is the generalized additive model, and we use the package regarding GAM. And so this, then this time we use the VGLM function, so generalized linear model function, and the party. So remember that the party. So this is the data set from the '96, the presidential election, and the party is so is the response variable, and the possible values are Democratic and Independent and Republican. So this is ordered variable. Then we use income. Income is basically here the numeric variable. Originally it's categorical, but the numeric variable. So we fit this party, so ordinal response variable, by we regress this bar on the income variable. Then we use this the cumulative. So since we are calculating probability of y is less than or equal to j, so this is the cumulative distribution function. Then parallel is false. Then we get the beta j x. So this the beta j depends on j. Then we use data, the RNES 96. We defined it in an earlier slide in chapter 7. So generally my slides are self-contained within chapter, but of course each page uses the code from the previous pages. Okay, so we have calculated this, and the first one is residuals, and then the coefficients are given here. So here the intercept, so this is theta 1, theta 2, and here beta 1, maybe I will say beta 1, 1, and beta 1, 2. So for two different models, so one is probability of y is less than or equal to 1, and the other is probability of y is less than or equal to 2. So we have only 3 values, possible values. So these 2 pieces of information is sufficient. And we estimated this theta 1, theta 2, and beta 1, 1, and beta 1, 2. And you can see that these variables are significant. And intercept, usually we don't really care much about it, but these are also significant. So here, actually the one variable, so it's not really, it doesn't look much more generalized than proportional odds model, but at least we can have the different estimate in the coefficient. So particularly the beta 1, 1 and the beta 1, 2 are different. So theta 1 and theta 2 are affected by the difference of the beta, but anyway, so these constants are in the model for the proportional odds model originally. And the next page is some statistics. So one is the residual deviance. So we have the residual, the degrees of freedom of 1884, and the deviance is 1987.5. So this should follow chi-square distribution if the model isn't much worse than the saturated model, the perfect model. So this is pretty good because the chi-square distribution, this follows chi-square. So this deviance follows chi-square distribution with this degrees of freedom, but this number is close to chi-square distribution. So that means that probably our model is not rejected against the perfect model. Yeah, so this is basically the estimate, and we have some other information such as log likelihood and the exponentiated the coefficients. So because so this is a kind of logistic model. So if we think about the exponential, it's easier to interpret the coefficient. in terms of log odds ratio. So now that we just think about this function again, and the last time that in the previous slide that we specified parallel is equal to false, but this time the true. Then the beta transpose x and beta j in the previous page, but this j will be dropped. So beta common. So b transpose x is always the parallel in the space of the predictors. So we again defeat this, but this is basically the same as usual, the proportional odds model. So we can get these coefficients, and this is actually exactly the same as the previous proportional odds model estimated by the POLR function. So we again fit the party on income, and so we can get these values. And since beta is only 1, so it doesn't depend on j for the usual proportional odds model. So here the negative the 0.01312. So this is just the one number. And the previous page, then actually it appears here. So actually the sign has been changed because the VGLM function, actually the g of the gamma j is equal to the theta j plus the beta x, maybe beta transpose x. This is the notation, but here the POLR function, as we discussed before, the g of gamma j is equal to the theta j minus the beta transpose x. So we have different coefficients, so just be careful. Actually, the proportional odds model, so this is a little bit strange because we have negative sign here. So it's actually a little bit special. And the VGLM function is just as usual, the theta j plus the beta transpose x. And you can see other coefficients are the same. So 0.209, 1.29. Also, maybe you can check the z value, 1.84, 10.76. And actually, these are exactly the same. So in this way, we can fit the usual proportional odds model with the VGLM function. And lastly, the testing. So this is the generalized model, maybe our model, so generalized, this subsection. And the first one is the usual one. So this is the regular, the proportional odds ratio, odds model. So the proportional odds model is smaller. We have the one parameter less. So remember that the theta j, the plus the beta j transposed x, and the theta j and plus the beta transpose x, and we have j is equal to 1 to 2, so we have just one more parameter for the generalized model. So the difference in deviance is negative 2 times log likelihood. So that has degrees of freedom of 1 asymptotically. So if sample size is large, this should follow chi-square distribution with df1. So we use chi-square distribution to calculate the p-value of this deviance, and the 7.82 is pretty large when degrees of freedom is 1, because the expectation is 1 under null hypothesis. And actually p-value is very significant. So that means the generalized model is better than the regular, the proportional odds ratio. So the model improved statistically significantly.